Quantum Physics at the National Research and Innovation Agency of Indonesia. And today I will be the moderator for this colloquium. And I would like to inform you that we organize our quantum physics colloquium twice every month, and we invite speakers from our research center and also guest speakers from the other institutions. For today, we are pleased to have Dr. Sunghun Park as our guest speaker from the Center for Theoretical Physics of Complex Systems at Institute for Basic Science, IBS, in South Korea. Dr. Sunghun Park will speak about the spin-orbit splitting of Andreev states in a Josephson weak link, and this talk explores the spin-split Andreev states in semiconducting nanowire Josephson junction as a potential qubits with long coherence times and high controllability, and it presents a theoretical model incorporating Rashba spin-orbit coupling and explains experimental observations in the circuit quantum electrodynamics, highlighting the potential of these spin states for superconducting qubits. So it's my pleasure to welcome back Dr. Park.
Thank you very much, Sophie.
Very nice to meet you again.
Nice introduction. I will share my screen now.
Yes, please. So let me also briefly introduce our speaker. Dr. Park has obtained his PhD in physics from KAI, South Korea, and he is currently a senior researcher and IBS Young Scientist Fellow at the Center for Theoretical Physics of Complex Systems at the Institute for Basic Science, IBS, in Daejeon, South Korea. He was also a postdoc at KAI, South Korea, and also at Technical University Braunschweig in Germany, and at Autonomous University of Madrid in Spain. His research interests are superconducting hybrid nanostructures for quantum devices, topological states of condensed matter, and electron transport in mesoscopic system. So with that, actually, Dr. Park, you will have 1 hour for the presentations and 30 minutes for the question and answer. But for all participants who wants to ask a question during the presentation, you can type your question inside the chat box, or you can raise your hand to directly ask the question to Dr. Park, and Dr. Park will answer your question during the presentation.
Thank you.
Okay.
Thank you for
yeah. So the time is yours, Dr. Park. Let's start.
Okay. Thank you for the introduction, and also thanks to Gagos and Adung for the invitation and the nice arrangement of this opportunity to give you a talk. Sorry for not visit on-site your nice institute, but giving you this presentation online. But hope to enjoy this presentation. As Sophie introduced, I will give you a talk about the spin orbit effect in a Josephson weak link, which was done with my former advisor, Alfredo Leviati, in Madrid, and the experimental group in Saclay, France. So I'd like to start with a brief introduction to a Josephson junction. Why it is interesting. The figure in the middle shows the superconducting quantum processor at IBM, where it consists of the superconducting qubit, the so-called transmon superconducting qubit, processing discrete levels as shown here, which is coupled to the superconducting microwave resonator. Here we encode the quantum information in this qubit and read out the qubit states by using this microwave resonator. This nano-sized processor operates in this energy scale of gigahertz, and the size of this processor typically from 10 nanometer to 1 micrometer. This the superconducting qubit studied to achieve to make a qubit with the long coherence time and the high controllability. If we zoom in this the superconducting qubit, then we see the very important circuit elements called the Josephson junction. So in this field, it is important to understand the physical property of the Josephson junction. Broadly speaking, there are two types of Josephson junctions. One is the insulator sandwiched by the two superconductors with the phase the difference between two superconductors is the delta. This is we call the Josephson tunnel junction and used in this the quantum processor at IBM. This Josephson tunnel junction has a simple relation between the supercurrent and the phase difference delta. And we can replace this insulator by some metallic material like atomic contact, nanotube, or nanowire. This the second type of the Josephson junction is called the Josephson weak link. In this case, the Josephson currents, the property of this the Josephson current depends on the materials in the middle. So if there is some material, whatever the material you are interested in, you can study this material property using this the Josephson junction structure. Here, among these the Josephson weak link, I will focus on the last one, this the nanowire-based Josephson junction. Here, the simplest model for this the nanowire-based Josephson junction is as follows. We have a superconductor, nanowire, and the superconductor structure. In this nanowire, the simplest theoretical model is just the one-dimensional parabolic bands. And in this superconducting region, because of the proximity effect to the nanowire, there's some superconducting gap delta around this chemical potential. So if we consider an incident electron from nanowire to this the interface between nanowire and the superconductor, then there's some phenomena which we call Andreev reflection. As shown in this figure in the right, this Andreev reflection occurs by converting the electron to hole, leaving Cooper pair in this superconducting region. So this the electron hole conversion process occurs at the both interfaces and form Andreev bound states localized in this nanowire region. Now, by doing some, sorry?
Can I
Yes.
ask a question, a simple
Yes.
one? So in the Andreev reflection, the electron comes to the superconducting and then reflected as a whole, and then we have Cooper pair.
Right.
Does the whole have the same energy with the incoming electron, or it's different energy?
It's the whole has the different energy. Here we have this the dashed line is the chemical potential, and the electron incident approaching to this interface has some energy epsilon above this the chemical potential, and this hole has the less energy than this the chemical potential, and the sum of these two quasi-particle is equal to the 2 times chemical potential. Okay, so this electron energy is mu plus epsilon, and the hole is mu minus epsilon.
And then the Cooper pair will be the mu.
Yes, the 2 times mu. Yes.
Yes. Okay. So
the sum of these two.
Yeah. So the energy is conserved during this Andreev reflection.
Exactly. Yes.
Okay, that's what I want to ask. So then
Thank
we
you.
have two interfaces here. So suppose we have electron coming to the right interface, and then the hole is reflected. Then the hole travels to the other interface in the left. Then it will be reflected again as into electron.
Right.
Also it will be many times multi-reflection, something like that. And does it create what you call the bound state? This multiple reflection.
There's some mixture of electron and hole due to these the Andreev reflections at the both interfaces, and by doing some boundary matching at the both interfaces of the wave function, then we can find resonant energy. Similar to the quantum mechanics problem, the single particle in a confined hardware potential.
Yeah.
Yes.
Okay.
So,
thank you.
Thank you. Thank you for the question. So if we find the wave functions in this normal region and the superconducting region, and matching these the wave functions at the interfaces, we get this transcendental equation from which we can find the energy levels of this the Josephson weak link. This equation has some physical parameters. Here the tau is the transmission probability, which characterize the scattering process of electron and hole in this nanowire. And here lambda, the dimensionless parameter lambda, indicates the length of the junction divided by the h bar v over delta, which we call the coherence length. So typically in experiment, the coherence length is about 100 nanometer to 300 nanometer gap delta. Now we solve this the equation and get this the energy epsilon as a function of the phase difference delta. Here the dashed line represent the energy levels for the ballistic case. No electron scattering, very clean. So electron and hole moves the back and forth between two superconductors without any scattering. If we introduce some scattering and consider some finite reflection in the propagation in this the middle region, then it breaks the degeneracy and shows the energy levels drawn by the solid line in this figure. Here, for the short length Josephson weak link with the lambda equal to 0, then we have only the single energy levels in this energy window. Now, if we increase the length, then these levels lower in energy, and more and more energy levels appear. It means that if we increase the length, then the separation between the energy levels decrease. Okay. So this is the typical dependence of the energy levels for the electron scattering and the length of the junction. So now for finite length, we have well isolated energy levels. So we may consider these energy levels as a qubit stage, right? Let me shortly compare this with the transmon, which is widely used in this superconducting quantum processor these days. This transmon use the bosoning mode of the circuit composed of this capacitor C and the Josephson tunnel junction. This transmon used lowest two levels, the ground and the excited in this energy levels, and typically this stage spread over the size of this circuit. For the case of this Andreev qubit, as I told you, that we use the Andreev stage localized in this Josephson weak link. So at most the size of this Andreev stage is the length of the Josephson junction, and it follows the fermion statistics. I mean, this Josephson qubit use the fermioning mode, right? So that this is the main difference. The history of this Andreev qubit is not quite long. For example, if we see the nice review paper by Michel de Bourret and the other big names, then there's some short comments that this stage in this Josephson weak link can be a candidate for this superconducting qubit, but we have a few experimental evidence. However, in 2013 and 2015, the experimental group, Quantronics group at the Saclay in France, reported the quantum effect of this superconducting weak link. They considered this mechanically broken superconducting atomic contact made by this aluminum, which has this two levels, the ground and excited stage, as shown in figure B, and shine the microwave to see the transition between these two levels. And they observed these transitions nicely with this microwave spectroscopy. And since then, people study these systems, and some increase the possibility to use this Andreev stage as a qubit. So we call this qubit is the Andreev level qubit. Okay. So far, I have not considered any the spin degree of freedom. So now we go one step further. by considering the spin degree of freedom in this the Josephson weak link. So our line is as follows. We consider the spin-orbit coupling in this nanowire Josephson weak link and explain how to read out this Andreev stage using this circuit QED. And I will finally show some experimental data about this. So let me give you some briefly the effect of the spin-orbit coupling on this electronic bands of the nanowire without the superconductor. Now we consider the nanowire, a realistic nanowire, which has some finite width, such that in this transverse direction, there's some confinement potential, as shown in this upper right figure. And for simplicity, we consider the lowest two transverse mode, M1 and M2. And the simplest form of the spin-orbit coupling is shown here. If we have a very thin nanowire, then the separation, energy separation between this M1 and M2, very large. So it is safe to consider only the lowest transverse mode, and we have the simplest the parabolic energy bands to describe this now if we include the first term of this spin-orbit coupling, this the minus alpha kx sigma y, then it splits the spin subbands, because this spin-orbit coupling term has the different effect for different spin, right? Now we consider the full form of this spin-orbit coupling on this thick nanowire. The thick means that the energy separation between M1 and M2 are not very large and come into play in this electronic bands. Because the second term in this spin-orbit Hamiltonian, alpha ky sigma x, do not commute with this first one, right? The sigma x and the sigma y. So it split, it breaks the degeneracy between the lowest and the second lowest transverse subbands and modify the electronic bands. This energy region where this modification is significant is what we are interested in.
Can I ask a question again, Dr. Park?
Yes, please.
I'm still not. I'm still not clear about why the thickness of the nanowire affect the, say, the number of level, the energy dispersion here. Yeah, why the thickness affect this?
Yeah, here what I mean by the thickness is that, for example, if you consider the electron confined in this the harmonic potential well, then the width of this harmonic potential, sorry, the confinement potential, the width of the confinement potential determines the energy spacing between the levels, right? Yeah, it inversely proportional to the scale of the width of the confinement potential. As you increase the
thickness
width of the
so then
energy spacing it decreased algebraically, right?
Okay, so we will have more
More
reverse.
yes.
And
If the radius of this the nanowire is the r, then the energy difference between M1 and M2 is 1 over r square, is proportional to 1 over r square. So if we increase the radius of the nanowire, then the energy difference decreased.
And also, I think we have a question from Dr. Hamza Fauzi. Maybe you can directly ask. Dr. Hamza.
Thanks a lot. Can you hear my voice?
Yes.
Right, okay. Thanks a lot for the presentation. I just want to clarify one thing. Normally in the nanowire, you have like Fabry-Pérot resonance.
In which direction?
In nanowire, Fabry-Pérot resonance between the contact from one end to another end. So there's a similar. You have this kind of like reflection that leads to the standing wave. Does this also affect your qubits?
Probably that there is, I think. But later we will attach the superconductor to this the nanowire, and in this the superconducting regime, the stage probability of the stage exponentially decrease, and I think this the Fabry-Pérot resonance due to the boundary of this the nanowire will not affect the energy spectrum of the Josephson weak link. I think that there is, but probably is very tiny energy scale which we can ignore in this discussion.
It's negligible. Okay, thank you.
Thank you. Here, in this modified electronic bands, what I want to point out is that we have two different Fermi velocities, V1 and V2. The outer channel electron has the Fermi velocity V1, and the inner channel has the Fermi velocity the V2. It is important because the energy of the Andreev bound states that depends on the Fermi velocity. If we consider this different Fermi velocity in this Josephson weak link, then we see a more complicated transcendental equation. Here we have tau and phase difference delta and epsilon as before, but the new parameter, the different Fermi velocity information are encoded in parameter gammas. Here gamma 1 is equal to the L divided by H bar V1 divided by delta, and the gamma 2 with the different velocity V2. Here, if the two variables, the gamma 1 and gamma 2 are the same, the equation recovers the previous case without the spin orbit. And now, if the two parameters are different, then we see this spin orbit effect in this the nanowire Josephson weak link. Here, I'd like to note that because of this modification, we can define the pseudo spin degree of freedom U and D, which is the combination of the real spin up and down and the transverse modes M1 and M2. If there's no hybridization between the transverse mode, this the U and the D, this the pseudo spin degree of freedom reduced to the this the real spin degree of freedom. So it is the broadly speaking some extension of this the spin degree of freedom in this the geometry. So now we calculate the Andreev energies of the bound states in this the Josephson weak link with some realistic physical parameters. Should the junction limit where L is equal to 0, we have a single degenerate energy level, which means that no spin orbit effect in this case. This is because if L is equal to 0, this gamma 1 is equal to gamma 2. So here we don't see any splitting, but if L is finite, then the levels start to exhibit the splitting between these two spin states. So if we increase further the length, then we see more pronounced splitting of these the energy levels. So people are now trying to detect this signature of this spin splitting and levels, and consider how to use these states as a new type of superconducting qubit. Okay. So this is the end of the first part, and any questions for this spin split Andreev states?
Any question from the participant? Maybe you can type the question now or just raise your hand. Maybe I will ask the question once again. So
Yes,
in the
please.
diagram of your Andreev reflection, I think in the previous slide.
In this introduction. Here.
Yeah, this one.
Yes.
So here you have a kind of 4 energy levels, but why you only consider 2 electrons in the lowest 2 levels, the black and the blue, but we also have another higher level, right?
We have higher levels, yes.
Yeah, but why do we only consider this black and blue electrons?
There are many, yes, and the short answer is that because that this is the minimal model. This is the minimal model for our purposes. In experiment, there are a bunch of lines, and it means that we need to take into account more electrons. But we thought that the minimal model with the 2 electrons, this the black and the blue, simple and enough to describe the main signature of the experiment.
Okay.
Yeah. So that this is only the reason. in order to quantitatively analyze the experimental data, we need to take into account the more electrons. You're right. But as a theorist, you know, we always try to find the simpler one. So that's only the reason.
Thank you. Any other question? Oh, we have a question from the participant. So from Dr. Emir. So let me read this question. Does the splitting through spin-orbit coupling unique to this fermionic state, or can we find similar effect in boson?
The answer is that I think it's the fermionic property, because typically the spin orbit coupling and spin degree of freedom affects the electronic bands or electronic transport if the quasi-particles are fermionic. But these days there are some studies that even in this the bosonic system, you may define some spin orbit coupling, and there's some related effects which I don't know well. But in a undergraduate level, I would say that this is the fermionic property. Yes.
So, okay. So he say thank you for the explanation.
Thank you for the question.
So what's the advantage of using this Andreev state qubit? I mean the fermionic state qubit compared to the transmont.
Yes.
What's the advantage?
I will probably stress later in this presentation, okay. But shortly speaking, currently the two main platforms for the solid state qubit. One is the superconducting qubit, and the second one is the spin qubit, using electron spin in a quantum dot. Roughly, the superconducting qubit has some property of easy to manipulate by using a microwave, but the coherence length is short. Sorry, coherence time is short. But the spin qubit has the opposite property. It has the long coherence time, but difficult to manipulate. Here, the idea of using the spin degree of freedom of the Andreev states is to achieve combining or taking some advantage of these two.
Okay, so the middle.
Yes, probably it could make some qubit with the long coherence time, which is the advantage of the spin qubit, and easy to manipulate, which is the advantage of the superconducting qubit.
Okay,
yes.
I understand.
This
we also have one more question from the audience. So Dr. Hasdio will ask directly, I think.
Oh yeah, hello Dr. Park. I hope
Hi.
you remember me. Very nice presentation. Can I have question? I remember reading the paper by Liang Fu. In that time, he also uses Josephson. I don't remember actually, but there is a superconducting state, and then he used this spin orbit coupling to make the superconducting diode. So by applying magnetic field in plane, then you can expect some, I don't know, non-reciprocity probably, way that the band structure actually divert.
Yes.
Not in the same way. Can you comment on this, or is it related to what you are doing or not? Probably.
Yes. Thank you for the question. First, I do not consider the magnetic field. I don't break the time reversal symmetry.
Yeah, sure.
And but in experiment, we can apply the magnetic field parallel or perpendicular to the nanowire direction. In that case, this spin orbit induced diode effect can be detected.
Okay.
The thing is that as far as I know, this combination of the spin orbit and the G-man requires the strong G factor. But in this here, the material I have in mind is the indium arsenide. So I'm not sure that if the G factor is the about the 10 at most. So I don't know if it is enough to induce the diode effect with this the in-plane magnetic field. But definitely here this is the platform to detect the diode effect.
Okay, thank you.
Thank you.
I think there is no more question until now. So please continue, Dr. Park.
Yes, now we jump to the theory for readout of the superconducting qubit using this circuit QED. This is the schematic diagram of this circuit QED, which consists of the two subsystems. One is the superconducting loop, here drawn by the black lines, including this Josephson weak link we discussed in the previous section. In this case, this phase difference delta can be controlled by the external magnetic field phi. The second subsystem is drawn by this magenta lines. This is the superconducting resonator. And it can be described by a harmonic oscillator. Now they are coupled inductively to each other, and in this case, because of the zero energy fluctuation of this resonator, it induced some fluctuation to the phase difference across this Josephson weak link. So in the presence of the coupling with the resonator, this HQC, the Hamiltonian for this weak link, transformed to the form in this way. This delta is replaced by delta plus some fluctuation. And this fluctuation is described by the sum of A plus A dagger multiplied by the strength of the fluctuation, which is typically a order of 10 to the minus 5 in experiment. Because this is very small quantity, we can expand this perturbation and get the coupling Hamiltonian between the resonator and the Josephson weak link. Here, this is the expansion up to second order, and we have a first order and the second order coupling between these two. Here, what we need to do, this FR is the bare resonator frequency, and we have this set of discrete energy levels in this Josephson weak link, and if there's a coupling between these two subsystems described by these coupling Hamiltonian, then it induced some shift of the resonator frequency. We can calculate this shift of the resonator frequency by solving this Hamiltonian, including this coupling terms. Because this coupling Hamiltonian has the information about the occupation of the quasi-particle in this Josephson weak link, and also the transition between the discrete level. This frequency shift delta Fy has this quasi-particle information of the Josephson weak link. So if we measure this quantity in experiment, then we know the quasi-particle in which states, in which qubit states are in now, or the transition from initial to final stage, and so on and so forth. Now that this is the some solution I obtained by solving this Hamiltonian. And here there are the two parts. One is the contribution from the first order coupling strength, which is already well known and used many times over the many years, and we call that this is the James Cummings model. Here, if we include the second order coupling, then there's some additional contribution in this the resonator frequency shift, and this is the full solution of this frequency shift. Now, as an example, let me apply this theory to this superconducting atomic contact. We have a ground state energy E0 and the excited energy E1, and quasi-particle is at the ground energy, and E01 is the transition energy between these two. Then in this so-called dispersible regime, where the transition energy is comparable to the resonator frequency, then the frequency shift can be described by this James Cummings model, and it is determined by the physical quantities, the transition energy E01 and the resonator frequency. But in this red region, which we call the adiabatic region, sorry, this is because we no photon exchange between the Josephson weak link and the resonator occur because of this different energy scale. This is why we call this regime as adiabatic. So in this regime, the resonator frequency shift is determined by the curvature of the energy levels where this quasi-particle is occupying. Okay. Now that this is the second part of the presentation, and if no further questions, I will go to the last part of my talk, and will give you some experimental data about this system.
I think, yeah, there is no question.
Thank you.
Yeah, please continue.
Now this is the image of the experiment, which was done by this Quantronics group at the Sapley. They used the indium arsenide nanowire. typically known to have a strong spin-orbit coupling. And we use the aluminum to form this Josephson weak link. The length of this Josephson junction is about 400 nanometers, and the width, the diameter of this nanowire is about 150 nanometers. Here we consider the side gate and apply some AC microwave to induce the transition between the Andreev levels. If we zoom out sorry, zoom out this setup, then this Josephson weak link is embedded in this larger superconducting loop. And we apply the external magnetic field and control the magnetic flux, and thus control the phasor difference between these two superconductors. This superconducting loop again inductively coupled to the resonator, as shown in this image in the right. And by analyzing the monitoring the change of the frequency of the resonator, we detect the qubit stage, where the stage of the Josephson weak link.
Sorry, can I ask a simple question?
Yes, please.
So what we want to measure is the shift of the resonator frequency, like this delta FR. Then
yes.
What information from the qubit can we get from this delta FR?
This this delta FR has many informations, and the simplest case, we know from the sign of this delta R whether it is in the ground stage or excited stage. If it is the shift is positive, the quantity is positive, then it means that the system qubit is in the ground stage. If it is negative, then it means that the qubit is in the excited stage.
Okay.
Yeah. This is the simplest case, and in our case, additional parameters, for example, the phase difference, and it's not simply the two level, but the multiple levels. So we need to analyze the delta FR carefully to see the more information about the stage.
Okay, thank you.
Yeah, it depends on the system you are interested
okay.
in. Yeah.
I think then there is one question, maybe. I think.
Yeah. So
yes,
I just want to clarify one thing. So in the experimental setup, looking at the figure here in this slide, so the qubit is controlled by the electric field, yes?
Yes, you're right.
Okay, so because it's terminated, I see. Instead of magnetic fields, you control it by the so it means that from the experimental point of view, this is maybe one of the advantage, because then you can apply like local electric field to control.
Exactly.
Okay.
Yes. Some people apply this AC electric field through the resonator, but in this case, they use the side gates.
Yeah.
I don't know which one is better.
So yeah, I think this is have some definitely some advantage because then you can apply local gating, something like that.
Yes.
Okay. Right.
Thank you.
Thanks. Yeah.
There is one question. So a question from Dr. Solihin. Are there any specific criteria for circuit dimension?
The criteria for the circuit dimension.
Yeah.
I think in this case,
maybe the length of the nanowire. What kind of the best length?
That's what I can comment on. Yes, the length here length is about 400 nanometer. I think from 400 nanometer to 500 nanometer. This scale is order of the superconducting coherence length.
So we need to compare with the superconducting coherence line.
Yes, the length should be less than the superconducting coherence length in order to see the quantum effect.
Okay.
As I told you, this the Andreev bound state formed by the Andreev reflection requires the maintenance of the coherence. So if the length is larger, then probably the coherence loose, and we don't see clearly this the formation of the Andreev bound states.
Maybe what about the thickness? I forget this.
Thickness, that's the additional dimension. If it's too narrow, then one-dimensional description is more favorable. Here, because of the finite width, which is order of the 150 nanometers, we see the two transverse mode in a energy range we are interested in. Otherwise, it will be very high in energy, so we can simply ignore. So we don't see any splitting of the Andreev states.
Okay, thank you for the explanation.
Thank you.
Please continue.
Yes. Before showing the experimental data, I will explain some non-trivial transitions occur in this superconducting system. Here, there are the two types of transitions. One is the single quasi-particle transition shown in this the lower panel. Here, initially, let me consider the quasi-particle occupying at the finite energy level. If we shine the microwave, then it induced the transition from a low energy level to high energy, and this is the nothing special. This is the well-known transition from one level to the other. However, if we shine the microwave to the stage, ground stage, there's something non-trivial. If the microwave induces the transition of this pseudo spin down quasi-particle from the ground to the energy level above zero, then we have a quasi-particle, and there's some hole in this the ground stage. This the annihilation of the quasi-particle here drawn by the empty circle due to the particle hole symmetry of the superconductivity. We can consider this as a creation of the quasi-particle at the finite energy. Because of this, the annihilate correlate the operators relation. So if initially we have a ground state and shine the microwave, then we see effectively the two quasi-particle transition. So this is we call the pair transitions. Now let's consider this the microwave spectroscopy by shining the microwave to the spin split Andreev levels. In this case, as shown in the middle, we have a bunch of transition lines. Here, the lines drawn by green indicates the single particle transitions, and the red lines for the pair transitions. This is not the experiment, just some all possible transition lines theoretically, and this is the experimental data from this the two-tone spectroscopy. Here the two means that we have two frequencies. One is the resonator frequency, and the second one is the driving frequency. Okay, here the resonator frequency is the 3.26 gigahertz, and this F1 is the driving frequency. So for this bare resonator frequency, as we change the driving frequency, we measure the frequency of the resonator and get this driving frequency versus the difference, superconducting phase difference delta. Okay.
Sorry, what? So this plot show the measurement of the frequency shift of the resonator?
Yes, this color actually indicates the shift of the resonator frequency, and these the lines are transition lines. So
okay.
Yes, here this this the color is the shift of the resonator frequency, and these the lines are transition lines. Is it clear?
Yes, but how do we identify which one is the pair and which one is the single transition?
Yes, that's quite tricky, and nobody knows exactly. This is the experimental data, and we compare this with the theory, and as shown in this right, and we have this four split lines, which quite similar to what we observed in experiment. Okay,
and I think before you told us that if the shift is negative, it means that the qubit is in the ground state, right?
Yes.
And then if positive is in the excited state. And what about
yes,
in here? Does the red color means the qubit in the excited state?
Sorry, no, the explanation I gave you was the singleton spectroscopy without the driving.
Okay, without the driving.
Without the driving, if we just couple the resonator to the qubit and measure the shift of the resonator frequency, then we know the information whether it is ground or excited state.
Okay.
Here,
And this
what we want to see is the whether the level is split or not. The existence of the spin-off splitting of the Andreev levels. In order to detect experimentally, then we need to drive the system and see the split lines, because these 4 green lines are describing the single particle transition from lower to the higher Andreev levels. And if there's no splitting, these the energies 1U and the 1D are degenerate. In this case, we don't see these the 4 bundle of lines.
Okay.
This is just a single lines.
Single line.
Yeah.
So now
because of this the splitting, we see these the 4 split lines.
Yes.
Yeah. This is the very crucial signature to demonstrate the splitting of the Andreev levels.
And what is the meaning of the sign of the delta F then?
Yes, that's the
what you will explain
very
next.
good question. So the by compare our theoretical expectation, we demonstrate that we observe the existence of this spin-off splitting of the Andreev level. This is the first message in this parts, and the second one is the Sophie they asked, what is the meaning of these colors? Here,
yes,
the transition energy is ranging from 15 to 20 gigahertz, right? And it is large compared to the resonator frequency, about 3 gigahertz. So in this region where the transition energy is very large compared to the resonator frequency, then we can consider this as an adiabatic regime. In this adiabatic regime, the frequency shift is determined by the curvature of
curvature.
Yes, curvature. If this comparable, then the resonator frequency and the transition energy, all those complicated parameters that come into play to determine the shift. But in this case, only the curvature of the energy levels contribute to the shift of the resonator frequency. So in this case, this blue means that the curvature is negative, and the red means that the curvature is positive. So this is the physical explanation of the color.
The curvature is the curvature of the Andreev states, right?
Yes, curvature of the Andreev state. Yes.
Okay. The initial state, right? I mean,
yes. Here, there's some delicate step to calculate this delta F1. In this case, the curvature of the initial Andreev energy and the final Andreev energy also contribute to the shift
delta.
So yes, in this case, we conclude that the initial stage curvature more contribute, and this color follows from the curvature of the initial stage. Yes, although the two curvatures of the Andreev levels contribute, but the more dominant one is the initial one. Yes. Here, you may notice that what we observed is the transition lines between the low manifold to the higher manifolds, not the transition within the manifolds. However, in order to use this stage as a qubit, then we need to observe the transition between these two levels within a manifold. But the experimental guys said that really hard to observe these transitions. It's very low in frequency, and we don't know exactly the mechanism what induced the transition between these two. So still many studies needs to understand experimentally and theoretically, but this is clearly the next topics in this direction.
So the experimental result, this experimental result consider all possible transition, not only that.
Yes, they sweep the driving frequency from 0 to 20 gigahertz. It should be less than the superconducting gap, but in this range we see all possible transitions.
But the experimentalists told us that we cannot really distinguish the smallest one. Difficult.
Yes, very difficult. When we discussed about this, there's some here in the middle. It's not clear whether there's some intramanifold transition or not, but the data in the right shows the very faint lines, which probably transition, the intra transition, but still it's not clear what determines how to increase this strength of the transition. This is still the remaining issue.
Thank you.
Thank you. So I closed my talk with the summary. I explained the possibility of the spin-orbit splitting of the Andreev bound stage in a Josephson weak link without the magnetic field. So it's clearly the time reversal. We do not break the time reversal symmetry, but still there's some splitting between the Andreev states, and we observed this and see the transitions between this split Andreev stage using circuit QED, and it's the first step towards the application of this stage to the use as a qubit. Okay, so now we need more detailed studies to understand how to induce the intrability transitions, and is there some mechanism in order to manipulate the stage, and also how to understand the experimental data whether the current theory is enough or not. Those are the some issues that I'm currently interested in. And thank you very much.
Thank you very much for your amazing presentation, Dr. Parks, about
Thank you.
the new type of qubits using spin split Andreev states, and which possess high controllability and longer coherence times. So now we will open question and answer sessions, although we already have a question and answer session during the presentation. So if any participants want to ask, you can raise your hand or type your question.
Yeah, raise your hand and open the mic. If
it's better.
Yes.
Any question?
Probably some students feel difficulty to understand this the big yes.
Yeah, so another question from me.
Yes.
Is there any demonstrations of coherent manipulations like Rabi oscillations and all?
Currently, yes. From Michel Deborah group at the Yale University, they report the coherent manipulation of this the Andreev spin qubits.
I see.
Yes, that yes. The thing is that yes, that as far as I know, that was the published I think 1 or 2 years ago. The first observation. But the thing is that we don't know which ingredient, physical ingredient, determines the lifetime of this the spin qubit. Still, there no theory supporting this experimental data. And as I told you, the motivation of this study is to make a long coherence time and easy to manipulation qubit, right? The data, the numbers in the paper, not very surprising, and need to be improved. Yeah, that's my impression. Yes.
Yeah, so I want to understand the transition mechanism. It seems to be still not so clear to me how you induce the transitions.
Yes,
in spin you induce the dipole transitions, but here you use the electric field and might be coupled to the charge.
What we understand in the phenomenological level is that if the system has the symmetry, for example, the conserve the quantum number for my pseudo spin, then this the transition not allowed. Only the spin conserve the transition allowed by the microwave. But in experiment, we see the 4 bundle lines. For example, here, and some imperfection or some structure of the experiment break the symmetry. For example, this the rotational symmetry of the nanowire or transverse symmetry, and here we suspect that this side gate, this gate applying this electric field, break the transverse symmetry and induce some mixing between these the 2 transverse modes. This is probably the mechanism why we see these the 4 lines instead of simply 2. Yes.
I see. Yeah. Okay.
Yeah.
I see. So it reminds me of the nuclear electric resonance. So where you have like quadruple moment.
Yes.
Demonstrated by
yes,
Citigroup,
probably
right?
yes. We can use some notations or some expressions that we can define this densities of the states as a dipole and the interaction with the microelectric field. Yeah.
Right. I see.
Thank you.
Thank you.
Any other question from the participants? So actually my research is about quantum battery. So maybe I can apply this type of qubit in my research for the quantum battery because it has long coherent times and also high controllability. So it's nice.
Well, I don't know well about this quantum battery, but you may be interested in the entanglement, right?
Yeah, if we have to.
Yes, as far as I know, the entanglement improves the property of the quantum battery, and you can charge it suddenly.
Faster.
Yes.
And also we want to keep the stored energy longer time, right? So we need higher, longer coherence time. So this type of qubit is good then.
Right, that's the important.
And also we want to be able to control the qubit, the quantum battery. So then
I see.
Qubit can also can be controlled easily. So it's nice information.
Yes, this is the probably one possible platform.
One
for
possible
this,
platform.
Yes.
Yeah. Is there any like the key challenges to make this kind of qubit in the experiment? The challenge, is it difficult to fabricate this kind of junction in the experiment?
The two junctions.
Yes, the nanowire in with this junction.
I think yes, we can make neighboring junctions in a single nanowire, or we can introduce the two junctions in a parallel way. I think this is the two ways to make two junctions. And in principle, it is possible. And I know the variety of the different type of the junctions from Copenhagen. Then there's some the center make many types of the junctions. They take a so-called mask technique. Dispute I think the gold atoms in a certain way to the nano wire, and the patterning this so any form of the structures that you want. So I think technology that we can make multiple junctions.
Okay. Then there is one question. It's from Emir. So how do we introduce entanglement in this type of qubits? So we have to kind of this two qubits. How do we introduce?
Yes. We need at least the two junctions. Then we can make I think entanglement, but in this superconducting qubit system, many ideas are already proposed how to make an entanglement. For example, this the flux qubit, and I think the transmon. There's some certain recipe with the three flux qubits. For example, how to make a entanglement with this multiple qubits. I think we can take this idea and apply this recipe to the junctions. The idea is that we have three parallel junctions, and the tune, for example, the length or gate voltage on the junction in the middle, and find some effective coupling to outer junctions. Then it may create the entanglement of the qubits, I guess. But we need more studies.
Yeah, and if we have two qubits, for example, using this type of qubit, what is the interaction between these two qubits? Is it dipole, or what is the interaction? I'm not really familiar in the
it depends on the probably dipole, or the if normally the capacitive coupling.
Capacitive coupling in the circuit.
Yes.
So can we control this? I mean, control this capacitor, then we can control the coupling.
Theoretically, yes, but some experimental list from the audience may complain this.
All right. So 4 more minutes before we finish our colloquium. Is there any other question from the participant? Students, for example, want to ask question? Yeah, basically, yeah, there are. Yeah, we have student already ask a question before.
Good.
Oh yes, for participant, please also check the chat box. There is a request to fill the form of the participation. Please check the chat box for the participant to record your attendance in this colloquium. Any other last question, final question? If not, let's finish our colloquium today. So thank you, Dr. Sunghun Park, for the presentation, for the this is very interesting presentation about new type of qubits that can.
Thank you very much.
That can
was
have
nice, and then many questions. I really happy to have this
you're welcome.
presentation.
Please come to Brin if you have a time.
Yes.
So thank you for all participants for joining us today. We greatly appreciate your participation, and we look forward to seeing you again in our next colloquium. So have a great day for everyone. Thank you again, Dr. Park.
Thank you very much.
Thank you.
Bye.
Thank you. Bye-bye.